Okay, hello. I will be working through the Are You Ready quiz for Module 2. Well, are you ready to say goodbye to Module 2, Unit 6? And some questions that are in both homework sets, Unit 6, Module 2A and B. So in this question, we're asked to rank the species that we'd expect to be in this solution of 1 times 10 to the minus 6 molar of barium hydroxide. All right, let's keep in mind that this solution is mostly in water, so water is going to be have the highest concentration. And what we're going to see is that barium, for every one barium, we have 2 hydroxides. So when comparing between C and D, this is going to make the essential difference. So there'll be H2O, then hydroxide would be the next concentrated, barium 2 plus. The acid form H3O plus will be even less present. It'll be less than 10 to the minus 6 because OH minus is higher than 10 to the minus 6. And then since we expect this to be a strong base, very little of the undissociated is present, which would be C. The second question, it was really about distinguishing between a strong acid and a weak acid. So let's just summarize strong acids. There's only 2 that you're expected to memorize, HCl and nitric acid, HNO3. And in this case, their individual concentrations, when you're given that, it's equal to H3O plus. So if you're given 0.1 molar nitric, you can immediately take the negative log of that, which will give you the value 1, and you know the pH of the strong acid. We can contrast that with the weak acids. There are 2 weak acids present in Unit 6, COOH, and the protonated amine. That's the other acid. So when you see a Ka, they refer to these 2 substances. In that case, they form an equilibrium. And in this equilibrium, we have to do an analysis of an ice table, or at least use the results of the analysis of the ice table to get the pH. Once we find, so here's the results of the ice table, the concentration of A minus and H3O plus is equal to the square root of Ka times the initial concentration. To remind you where these results came from, we can construct the ice table, which I'll do quickly. So we have the initial conditions of HA, which were given, which is 0.15 molar. We don't really care, are not concerned about the concentration of water. We assume that's constant. There are no A minus. There's no A minuses before dissociation here. And all there are 1 times 10 minus 7 molar H3O plus from the autoionization of water, which we will exclude, but we write in the initial step. The change is that minus X, so there's going to be some change in HA that's going to form both A minus and H3O plus. The equilibrium condition is the sum of both, so we just add I plus C, and we get these values. This is strictly correct, but for our class and given our significant figures, we're going to make an assumption that we can exclude the 1 times 10 to the minus 7 from that sum, and the difference, so 0.15 minus X, is also negligible. And then we can plug this into the Ka expression, and this is where we get our ability to solve for X, which is both A minus and H3O plus. Gives us the square root of Ka times the initial concentration, which we talked about above. We do that, and we see we get X is 1 times 10 to the minus 3, approximately, giving us the pH of 3. So now that we know that the pH equals 1 for nitric acid, pH 3 equals pH 3 for this concentration solution of acetic acid, or the CH3COH, we can pick B. All right, and the next question is designed to rearrange the equilibrium expression into something that gives us the ratio of the conjugate base to the acid. So initially in Module 1, we started off with Ka in this form. Is very useful for determining concentrations of the species. especially determining the pH given a Ka, an initial concentration. But for questions like this about the ratios of weak acid to its conjugate base, it's much more convenient in this form, where we see that Ka, the ratio of Ka to H3O plus, will give us the ratio of A minus to HA. So pKa is given as 10.45, pH is given as 10.3. The pKa was 4.5 and the pH was 3. This gives us a Ka of 10 to the minus 4.5 and a H3O plus concentration of 10 to the minus 3. We plug these into the equation and we get the ratio. It should be 10 to the minus 4.5 divided by 10 to the minus 3, but this is about 0.03. So about 0.03, about 3% is A minus, which is the ionized form of the acid. So we mostly have HA. It's much bigger. It will be the dominant form. And then the answer is B. Alright, so question 4 and 5 are about the shifts, making sure you feel comfortable constructing the kinetics argument and the thermodynamic argument. Here we're constructing the kinetic argument. Here we have the acid, acetic acid, and the conjugate base plus H3O plus, and we're asked build the kinetics argument upon the addition of the conjugate base, a product. So we do that. The first step we have to do is construct the rate laws. We know that initially, before anything is added, the rate forward equals the rate reverse. So before we add any substance or at equilibrium, the rates are equal. Then step 2 destroys this equality by the addition affects one side more than the other, destroys the equilibrium. In 3, the system responds to reestablish or restore the equilibrium. Alright, so we're adding CH3CO minus, which is the conjugate base, A minus, which is a product. We increase the rate reverse, since the rate reverse involves the CH3CO minus times H3O plus. That corresponds, so the rate reverse increases, so there's a corresponding shift to reactants. So we expect that the reactant concentration should go up, and both product concentrations should go down in step 3, which is the response of the system to restore equilibrium. We would expect that H3O plus would go down, making pH go up. That was not asked for, but you should always be prepared for that question. And that gives us C, that the rate reverse will increase and shift to make more reactants. Okay, so we're now going to use the thermodynamics argument to explain what happens when we add OH minus hydroxide to this equilibrium. So we start with the same equilibrium as the last problem. And now we see that there's no direct connection to the addition of OH minus. It's not adding to any one of the 4 species shown. But what it is going to do is react with H3O plus and remove that from the solution. By removing that from the solution, we will see, and since H3O plus is a product, we will see an effect on the reaction. So initially, Q equals K. Anytime you're dealing with thermodynamics, you need to construct Q. And initially, before anything's added, for any disturbance, Q equals K, we're at equilibrium. We build the equilibrium expression here. So this is the quantity that we'll be monitoring. 2, the addition of OH minus. And the addition of OH minus will react with H3O plus to produce water. By the removal of H3O plus in this manner, we see that the numerator, which contains H3O plus, will go down. So in step 2, Q will immediately go down. So if we construct a curve of Q, and there's a very specific value of Q, which equals K, in step 1, So we have, let's see, step 1. It's oscillating around K. Then we have the event where we add OH minus, Q goes down sharply. And then we have the response of the system, which is to increase Q. Right, the response of the system is to increase Q. That means it's going to increase numerator, decrease denominator. So it's got to make more products, less reactants. So we expect the concentration of, and in this response only. In the response, the shift will make more H3O plus, more conjugate base, and less of the acid. But overall, the solution becomes more basic because we've added a strong base to the solution. The H3O plus, what in step 2 was removed. There's a slight adjustment of the system to make a little bit more, but it never makes the same amount that was initially reacted. So overall, whenever you add a base to a solution, it will become more basic. Anytime you add an acid to a solution, it will become more acidic overall. But the response of the system can be in a different direction. More basic, but the shift makes a little bit more H3O plus. And if we look at the answers, this would be Q. Q rapidly decreases, and then to reestablish equilibrium, the acid will increase, or the H3O, the anion, the A minus will increase, and the acid will decrease. Okay, so here is, so we did this problem, or a similar problem in class. So let's make sure there are no problems here. Alright, so we're shown an acid with 3 different acid-base functionalities with pKa's. And so the question asks, in this particular form that's shown, what must be the pH? And then if we wanted to ionize the side chain, at what pH should the pH, what pH should be used? So what we're going to do is we're going to build our, so let's start off and identify, because there's 2 carboxylic acids, so we got to distinguish them. We'll call the one with the lowest pKa Roman numeral 1, COH, the side chain COH2. And what we're going to do is put this on our pH line. So pH is increasing across the right. And what we'll do is we're going to mark as 3 specific pHs that we're going to be very interested in. So let's do that. We're going to be interested in the pH when the pH equals each of the pKa's, starting with the lowest one first and moving to the right, higher ones. So here we have 2.2 on 1. That's the pKa. We'll fill this in. So 4.1, and then the pKa of 9.4. So that was of the NH3 plus acid, right? So if it's an acid and pKa and there's a nitrogen involved, it has to be protonated with a positive sign. COOH, and that's Roman numeral 2, and COH Roman numeral 1. And so what we do is, to the far left, all species are always going to be in their protonated states. Okay. How do we know that? That's because that if the pH is less than pKa, the acid form dominates. Right? So that's what we talked about this in class in terms of the analysis. You should be able to convince yourself that means that the Ka over H3O plus is less than 1. If it's less than 1, then you have more HA than A minus. So since we're on the left of 2.2, the pH is going to be less than all of the other pKa's were in the collective at all acidic form state. But as the pH goes up past pKa, past one of the pKa's, right? pH is going to be greater than pKa, then A minus is going to dominate. And so we'll see that immediately as we cross the pKa, as pH crosses the pKa of COOH1, because we will now see A minus present for Roman numeral 1. Now pH is greater than 2.2, and Roman numeral 1's conjugate base will now be more concentrated. It will leave Roman numeral 2 unaffected because we're still below pKa of 4.1. And it will leave the protonated amine alone because we're still below 9.4, which is the pKa of pH 3. Then we go to a pH greater than 4.1. Of course, Roman numeral 1 is still in its basic form. Now we have the basic form of Roman numeral 2 at pH greater than 4.1. And since the pH is still lower than 9.4 in this region, we see that that NH3 plus is still protonated. As we go to the pH greater than 9.4, we have the individual carboxylic acid conjugate base is still present, and now we have the basic form of the amine NH2. The picture shows a protonated, both carboxylic acids are protonated, NH3 plus is protonated, so what we see is the pH less than 2.2 where all acids are present. Then we see that the pH necessary to have the side chain, which is Roman numeral 2, ionized, has to be a pH greater than 4.1. Using this information, we would pick B. Okay, so it's a really important analysis. Make sure you feel comfortable with the pH versus pKa arguments. So that ended the quiz. So now we're going to go through some of the characteristic homework problems that you're responsible for. Some troublesome ones that I get a lot of emails about. So let's do that. First one involves just a generic ice table of a KB. Just want to make sure if you have any questions about that you can see one worked out slowly. So what we'll do is we want to know the pH of a weak base, where we're given Kb 4.9 times 10 to the minus 6, and we're given an initial concentration. So anytime you're given Ka, an initial concentration, you should think ice table, or of course the results of the ice table, which are the square roots over concentration times K. Alright, so let's do that. Kb, and keep in mind that Kb for our class is either A minus or B. Right? A minus is going to be COO minus. It's going to be the conjugate base of the carboxylic acid. And B is going to be the neutral amine. Those are the only two bases that you're responsible for in Module 2. Alright, so we can write the generic Kb reaction, which means that the base reacts with water. Water is acting as an acid. It protonates the base, and so BH plus is now the new acid. And the product is OH minus. Writing the ice table, we write the initial concentrations of all the species. The change, which is that some of the base will react to form BH plus and OH minus. And then we make the following assumption that the 0.14 minus x is really just 0.14, and x plus 1 times 10 to the minus 7 is really just x. And we can plug this into Kb. And we get x squared by 0.14 molar equals what Kb is. X now is the concentration of hydroxide ion. It's also the concentration of BH plus. And we plug this in, and we get concentration to be 7.93 times 10 to the minus 4. So we have the concentration of hydroxide. The question asks for pH. There's a couple different ways to do it, but what I like to do is take the negative log of this number to get POH, and then just subtract that value from 14 and get pH. So POH minus log here, and so it's 3. So POH is 3.1. So pH would be 14 minus 3.1, which is 10.9, which is indeed a basic solution. Right, so it's a good thing to check just to make sure, if you put pH equals 3.1, that's an acidic solution. So there's no way we should be working with a weak base and put that in water and get an acidic solution. So POH is 3.1, pH is 10.9, so we put that value there. Okay, the next question asks, here we have a mixture, right? We're so used to looking at water as the only other species present, but you can mix weak acid and bases together. So this question asks you to think about that. So the conjugate base of acetic acid, which you should feel comfortable now after seeing it so much, is going to be that you remove the proton, you have COO minus. So that's the base. Anytime you have a base, you have to have an acid, and so the acidic form of NH3 is going to be NH4 plus. And what we're given is Ka, so the acid and base on the left-hand side, right? So you have the HCOOH and the base with the neutral amine. And then you have their corresponding conjugates, the base CO minus and the pronated amine, which is an acid. And so the question asks, so that's the chemical reaction that we just filled in. The question asks, well, given these Kas of the different acids, one on one side, one on the other, is this product favored or reactant favored? Well, if we look at the CH3, Ka is 10 to the minus 5, right, for the carboxylic acid. And if we look at the pronated amine, the Ka is 10 to the minus 10. So we see that the COOH, the carboxylic acid, is 5 orders stronger than NH4 plus. So we would expect that the reactants would be much more reactive, right? So it's much stronger acid than the acid in the products. So we would choose this to be product favored. It's going to be product favored because the strongest acid is, wherever the strongest acid is, the other side is going to be favored because the stronger acid means it's more reactive, and so always the other side of the equation will be favored. Okay, or you could imagine, so whatever side that has the weakest acid would be favored. So there's a lot of different ways to think about it. The main thing is to be able to construct an argument and why. Okay, so here we have a chemical equilibrium problem. We're given the equilibrium K value. And so we construct it. These are gases, but we can, of course, we can use the Kc version. We could also use Kp, but we're using Kc. And we construct the equilibrium expression for K. And so each of these events, so there's like in the blue boxes are these initial concentrations, and the idea is, well, what happens? What's the shift? Is it at equilibrium in these concentrations, or will the system respond in a way to establish 15, right? Because what it's going to do is it's going to establish 15, and so the goal is to plug these values in and say, do we have 15? Is it less than 15? Is it more than 15? If Q, when we plug in these individual values, if it's less than 15, what we're going to see is there's going to be a shift to the right to make more products. Since the products are in the numerator, so if Q is less than K, we will see a shift to the right, shift to products. Q is greater than K, we will see a shift to the left. That means there's too many products compared to reactants. Products need to reduce, reactants will increase. That shift is to the left to reactants. And then, of course, if Q equals K, there'll be no net reaction. We'll just see a system in equilibrium. So now we just need to do is plug these numbers in. So let's do that. 0.12 squared, 0.7, 0.6. That's supposed to be squared, of course. And we get 0.06. And then we do the middle one, 0.6 squared for SO3 divided by 0.6 for oxygen, 0.2 squared. And then we do the same thing for this one, right? So we do this for each one, and what we see is that the 0.06 is less than K, so this value Q is less than K. The middle one is exactly K, and the one on the right is greater. That value Q is greater than K. So now we just need to put these in the appropriate boxes. This will be a shift to the right because Q is less than K. This will be no net reaction, and then when you have 80, then we expected to shift to the left because Q is greater than K. Alright, so shift to products, no net reaction, and then shift to reactants. So it's really important to feel good about constructing these arguments, making sure you can explain that the thermodynamic argument of the way Q will respond how the system will respond to reestablish Q equals K. Okay, so this is a problem that tends to give a lot of people trouble, so we want to go over this in detail. You want to be able to, if you have any questions about this, you want to make sure that you can reproduce this analysis. We have a solution, a basic solution, and now we're going to evaporate the solution. It's left out in the sun, water's reduced, and so what happens is the concentration of all the species present are going to increase. So for the rates, all the rates forward and reverse, they're both going to increase, but we need to evaluate which one will increase more. And the same with Q. Q is going to have products over reactants. They're both becoming more concentrated by the evaporation, but we need to look at the magnitude change. Is the numerator changing more than the denominator? All right, so let's do that. In general, because it's a basic solution, the pH is going to go up, right? So you have a basic solution, you're increasing the concentration of hydroxide ion. You have a basic solution and you're making it more in general, the overall effect will make the solution more basic. Right? You're concentrating a basic solution, it's going to become more basic. You concentrate an acidic solution, it becomes more acidic. And of course, vice versa. The acid solution becomes more acidic if you evaporate, and the same with the base. Okay, so pH increases. But let's make the arguments, the kinetic and thermodynamic arguments in terms of the prediction. All right, so we have an event, and let's think about the kinetics and thermodynamics, right? Because the event is that a bunch of water has now disappeared and the system is no longer in equilibrium, and then we'll reestablish equilibrium. So the rate forward, which only involves one species, right, the reactants, that'll increase on evaporation. And the rate reverse, but this involves two species now. They're both going to increase, right? They're both going to increase, and so the net effect here is that there's going to be a shift to the left. There's going to be a shift to reactants because both products are increasing. The reactants are increasing, but it's not going to be as much as the products, so we see a shift to reactants. That means that NH3 plus, which are products, and OH minus will go down, right? The products will go down and the reactants will increase. This is the third step, right? So initially it's at equilibrium. 2, we evaporate the water, and 3, the system response. So we see the system response is the shift towards products. OH minus will go down after it's initially concentrated. So we'll see that even though OH minus goes down a little bit in the shift, the overall effect is the solution is still basic, is more basic than before. But these are the shifts that occur after equilibrium. The thermodynamic argument, we have to construct Q, and we see the same effect, right? That if the product, there's two species in the numerator, only one species in the denominator, Q is going to increase, right? So in this event, Q will increase. The shift in equilibrium is to reduce Q. You reduce Q by reducing products and increasing reactants. So Q must decrease. All right, and so what we're going to see is that we have an overall more basic. So the reactants are going to increase and the products are going to decrease. So this is the same story as the kinetics argument, it's just a different way. So we see that there's an initial concentration spike of OH minus, it makes it much, much more basic, but then the shift in equilibrium, because of the increase in OH minus, we see the shift occurs, and we see that the products go down and the reactants go up. So it's a really important analysis to be able to construct, and here it is. So please ask questions if you have any in class, office hours, or SI sessions regarding this analysis. Okay, so this is a similar question like the quiz, except the side chain doesn't have a carboxylic group, but it does bring up some of the issues you might face in sapling. So I'd like to go through it. So we see that we have a carboxylic group and an amino group, and we're asked, these three different pHs, what structures would be present. So just like the other problem, we're going to divide our pHs up by the pKa's. And to the left, we expect the acidic form to be present, and if the pH is to the right of the pKa, then we expect the basic form to be present. So we make the table, and we see that when we're to the left of both pKa's, we see both acid forms present. So that means that when you're in sapling, you have to add an additional proton to the amine and put a positive charge on the nitrogen. You leave the carboxylic group alone because it's in the acidic form. Right, and pH 7, we cross, it's now higher than the pKa of the carboxylic acid, but still less than the pKa of the amine, the protonated amine. So we see that we have CEO minus and NH3 plus. And when we get to be, when the pH is higher than 9.7, which is higher the pKa of the protonated amine, we have the neutral form. So going in here, we still have the 3 with the plus on the nitrogen, but at pH 7 we have to remove this H, right, because we're now in the conjugate base, the dominant species, and you have to add a minus sign on the oxygen. And 9.7, we can leave the amine alone now because it's in its basic form, and we just do the same thing, remove the hydrogen and put a negative charge on oxygen. So this is a kind of a feature in sapling where you have to make sure that you click on the nitrogen and put a plus sign, add the hydrogen. It's not going to add the plus sign for you. The same with the oxygen, remove the hydrogen. It's not going to automatically put a negative sign there for you. So keep that in mind. There'll be many other problems like this throughout the semester. Okay, so here's a question about how someone can ask for ice table information, even though it doesn't say, it's not just the general concentration Ka type of question. So to ask what's the percent ionization of a weak acid given a Ka and a concentration. So that means that step 1 is we're going to need to know what is the concentration of the ionized form, right? So we want to know how much has ionized from the neutral acid, right? And we want to find the percent, which is going to be the concentration of A minus divided by HA plus A minus. So 50% ionized, then A minus and HA would be equal. Or, and so we'll see, so step 1 is to find out what A minus is. We know what HA is. HA is already 0.11 molar. So we need to know what A minus is. Well, finding A minus is an ice table activity. And we'll do this fairly quickly because we did many examples. If you were just sort of skipping over to this and you have any questions about the ice table, go back into the previous questions, slide 2 and 3, where we do it fairly slowly. Okay, but we see that the equilibrium is going to be 0.11 and x, so we get x times 0.11, we set this equal to Ka, and we get the concentration of A minus to be 5 times 10 to the minus 7. 5 times 10 to the minus 7 is the concentration of the A minus, which is the ionized form of the acid. So this is the concentration of the ionized form. So to find out what the percent ionization is, we say, well, what fraction is that amount versus the initial amount of 0.11? We do that, and we see that it was 4.7 times 10 to the minus 4% ionized. And this is common with a lot of acids and weak bases, is that their conjugates are in very low concentrations when you put a pure acid or weak base in water. The conjugate is very low in concentrations. These are not recipes for buffers. A recipe for a buffer is going to have equal amounts of the acid and conjugate base. And as we see here is an extreme case, but we don't have equal amounts. We have 0.11 molar of the acid and only 5 times 10 to the minus 7 molar of the conjugate base. So this is not a good buffer, and we see that this is the acid dominates at this state. Okay. So the next question is going to be about buffers. So here we have what should look more familiar for a buffer, right? So we have some amount of millimoles of the acid, some amount of millimoles of the base, conjugate base. It's not quite 50-50. It's actually 60%, 60 millimoles, 60% acid and 40% base. But this still is in the buffer range. And we're asked, what is the pH of this buffer? Well, this should be pretty straightforward. And remember, keep in mind, buffers are always going to obey the exact same equilibrium expression that we've been using for weak acids and weak bases. It's just that it's oftentimes more convenient to use the logarithm case. So we take the negative log of both sides, and we see that pKa minus pH equals the minus log of the ratio. And so this is what we see. We have three quantities. We have the ratio of A minus to HA, we have pH and pKa. And what you're going to be given is 2 out of the 3 and asked to calculate the third, right? So here we're given the ratio, so we know the logarithm on the right. We're given Ka and we're asked to solve for pH. So we do that. 4.2 minus pH equals minus the log of 0.04 over 0.06, right? So we're given the right-hand side, we're given pKa, we just have to solve for pH, and we do that, and it's 4.38. But what if that's not the buffer, exact buffer we needed? What if we want to adjust the ratio? So now we see that that's not the pH you want. pKa cannot be adjusted unless you change the temperature. So we have, so we want to adjust the pH to a different one at 4.93 because the buffer in this particular state is 4.38. So we're going to do that by adding some sodium hydroxide. So let's walk through how we would do that. So we have the exact same expression, logarithm A minus HA. And now we're given the pH, right? So 4.93. And so now it's really about, well, what is the ratio of A minus to HA need to be so that we can achieve this pH? And so that means that by adding a base, keep in mind the shifts, adding a base is going to reduce, right? It's going to reduce the acid, and it's going to increase the conjugate base. So we're going to see the numerator increase, which is the conjugate base, and we'll see the denominator decrease, which is the conjugate, which is the acid. So we would write this down. We don't know how much it's going to decrease, but what we see is that some of this is going to increase, right? So the numerator is going to increase, and the denominator is going to decrease, right? We expect that when we add the OH minus, it's going to decrease. So this is a good model for analyzing how a buffer is adjusted. So we have OH minus reacting with HA to make A minus. So every mole that we need to adjust this ratio has to come from OH minus. That's how we're going to know what volume we need to add. So it's going to disappear from HA and appear as A minus. So let's see what quantity we need to adjust. So by subtraction, we see that 0.073 on the left of the reaction is equal to this log. We have to get rid of the logarithm to do the algebra, so we'll take 10 to both sides. And if we do that, we see 5.37 is going to be equal to this ratio. So now we just need to solve for x. It's a pretty straightforward algebra problem now. We just multiply both sides by 0.06 minus x and set it equal to 0.04 plus x. We can then distribute the 5.37. And when we do that, we get this expression. We put all the x's on one side, all the constants on the other. And we get x is 0.04. Right, so that's the quantity that we have to add to the numerator and subtract from the denominator to get the right ratio, so that when we take the negative log, we get the new pH that's desired. So this shift has to come from the moles added from sodium hydroxide. So given that we have 5.5 molar sodium hydroxide, how many mils would that correspond to? So we do that up there. So we want to deliver 0.044 moles of sodium hydroxide out of a 5.5 molar solution. So we just take the reciprocal of the concentration now, so moles will cancel and we'll be left with liters. And we get 0.008 liters, which turns out to be 8 milliliters. So 8 milliliters of sodium hydroxide, when put into this buffer, will shift it from a 4.38 pH buffer to a 4.93 buffer. It's a very important laboratory technique, and this are the steps. Okay, so here's a grand summary of Unit 6, Module 2. It probably sounds like a lot of information, and it is, but if you characterize it and see it in terms of thirds, then it might be more easily managed. So let's do that. So here's Unit 6, Module 2. And so the first third, second third, and third third. Okay, so the first third is about the initial concentration and the equilibrium constant. At what pH do you have, if these are your initial conditions? You have an acid with a certain Ka or Kb at initial concentration. Right? So this was the case. It reacts with water, produces an ice table. You can find out what it will be the equilibrium concentrations of all the species based on this information using the ice table. And so that's the goal. And so you want to make sure that when you see those kind of questions that you can answer, you see C0 and Ka, you know exactly what to do. You're probably being asked the pH or you're being asked the concentration of a hydroxide. But in the first third of this module, these were the types of questions, and they're fairly straightforward. So pH, pKa. In 2, it's a much more complicated conceptual argument here about what happens to the equilibrium once something is added or removed. So you had 2 different Ka reactions, so you should make sure that you feel comfortable with both of these Ka reactions. This is either the pronated amine or the carboxylic group. And then you have 2 Kbs, which is the conjugate base of the carboxylic group, or the neutral amine here. And so in this second we said, well, what happens? So HA is COH, A minus CO minus, B is NH2, and BH plus is NH3 plus, right? And so now in this second third, we're asking you, there's 4 possibilities in the chemical equilibrium that you're responsible for. What happens if you add or remove substances? So you need to construct arguments using kinetic and thermodynamic arguments, adding water, adding A minus, HA, adding a strong acid, which will add H3O plus, adding a strong base, sodium hydroxide. And we did this on many other problems in this video. So if you have any questions about that, make sure you look at that. So you're responsible for both the shift in equilibrium that occurs and the pH effects. In the last third, it's about constant pH environments and what species will be most present at a certain pH. In this case, we rearranged the equilibrium expression to be much more manageable for us. So we have Ka, which is a constant divided by the hydronium ion concentration, which is adjustable in the lab, and we see that that tunes the ratio to A minus to HA. We could also take the negative log version, and we get this, which is famous, called the Henderson-Hasselbalch equation. So a 50% buffer is made when A minus is the same as HA. This does not occur normally when you have pure HA or pure A minus solutions. You do not make buffers that way. You have to add some concentrated acid or base to react with half the number of moles to get a 50-50 buffer. So equal moles here will produce the highest capacity buffer. The pH will equal the pKa at this point. And so this is a nice summary of all of the Unit 6 Module 2 information you're responsible for. Please make sure that all of the 12 slides presented here is a total of about 14 different problems, that you feel comfortable with all of these. And if you do not feel comfortable and after seeing these solutions you still have questions, please do not hesitate to ask.